This conference will now be recorded.
Good evening, everyone. Success usually comes to those who are too busy to be looking for it. Do something today that your future self will thank you for. This is Josanita from the Department of ECE of Loyola Institute of Technology. Takes immense pleasure to welcome you all for this wonderful webinar on public key and hash algorithms. Prayer should be the key of the day and lock of the night. I invite Mr. Johnny Lincoln and Miss Harita to lead us with a word of prayer. Over to you, Johnny.
Bible reading. Today's Bible reading taken from the book of Proverbs, chapter 21, verses 30 and 31. No human wisdom or understanding or plan can stand against the Lord. The horse is prepared for the day of battle, but the victory belongs to the Lord. This is the word of God. Thanks be to the Lord.
Lord's Prayer. Our Father, who art in heaven, hallowed be thy name. By thy kingdom come, thy will be done on earth as it is in heaven. Give us this day our daily bread. Forgive us our trespasses as we forgive those who trespass against us. Lead us not into temptation, but deliver us from evil. Amen.
Thank you, Mr. Johnny and Miss Harita. Small cheer and great welcome makes a merry feast. Welcome the challenges, look for the opportunities in every situation to learn and grow in wisdom. I welcome Miss Shiny to welcome our chief guest and to address the gathering. Over to you, Miss Shiny.
Thank you, Miss Josanita. Good evening to everyone gathered here. I hope all are safe and doing good. Thanks to the Almighty God for keeping us safe during this crisis. Now it's my pleasure to extend a cheerful welcome to you all, and on behalf of Loyola Institute of Technology Management, Administrator, Principal, Vice Principal cum HOD of ECE Department, we wholeheartedly welcome all the participants for this webinar. On behalf of the department, we the coordinators welcome our resource person of today's session, Dr. S. Bhagavati Priya, Professor in Department of Computer Science and Engineering, Rajalakshmi Engineering College, Chennai. It's my pleasure to extend a cheerful welcome to you, ma'am, and your presence makes us very happy. And I'm sure that we'll be enriched by this webinar on public key and hash algorithms. Thank you so much, ma'am, for accepting our invitation even during this pandemic. We welcome you wholeheartedly for this webinar. In this context, I also congratulate all the coordinators of this webinar, faculty members of ECE, and professional friends to make this happen. Dear participants, once again I welcome you all for this wonderful technical day. Thank you. Over to you, Ms. Joshanita.
Thank you, Miss Shiny. I call upon Miss Hemalata to introduce our speaker of the day. Over to you, Miss Hemalata.
Thank you, Mr. Srinita. A very glad welcome to one and all gathered here. I am Hemlata from the Department of ECE, and it gives me an immense pleasure to introduce our resource person, Dr. S. Bhagavati Priya, a professor of computer science and engineering at Rajalakshmi Engineering College, Chennai. She has received a gold medal in MTech degree, and she received a PhD from Jawaharlal Nehru Technological University, Hyderabad. She has 22 years of experience in teaching and 15 years of experience in research. She has guided 9 research scholars. She has published around 50 research papers in various conferences and journals. She is the author of the book titled as Operating System. She has published 3 book chapters in IGI Global, CRC Press, and Billy Publications. She received Best Paper Award in ICTIS in 2015 at Ahmedabad and CAASR International Conference 2017 at Dubai. She received the award of Top 20 Influential Women Educators in Tamil Nadu from the Academic Council of Euclids. She received Active Participation Woman Award from CSI. She is a life member of CSI and IAENG, and now she is with us to make this session more interesting and knowledgeable. We gladly welcome you, ma'am. Over to you, Ms. Joshinita.
Thank you, Ms. Hemalata, for the brief introduction you gave. We are pleased to have you with us in this webinar, ma'am. Thank you for your presence. Listening is a positive act. You know how to put yourself into it. Now we have come to the most awaited session of the day. Let us listen to this webinar on public key and hash algorithm with the intent to understand, not just to hear. I request Dr. S. Bhagwati Priya, Professor in the Department of CSE at Rajalakshmi College of Engineering, to take over the session. Participants, if you have any queries, kindly post it in the chat box. It will be answered at the end of the session. Over to you, ma'am.
Thanks for the nice introduction. Good evening to all. First of all, I thank the organizers of this webinar. My sincere and special thanks to my beloved professor, Dr. Nalini Joseph ma'am, for inviting me to this webinar. Let me start the session. In this session, we are going to see public key and hash algorithms. First of all, we are going to see the Chinese remainder theorem. The Chinese remainder theorem is a theorem which gives a unique solution for simultaneous linear congruences with coprime module. So you know how to solve a single linear congruence. Already you have studied how to solve a single linear congruence. In this session, we consider how to solve a systems of simultaneous linear congruences. So here we have three congruences: x congruence to a1 mod n1, x congruence to a2 mod n2. This is the general thing. N1, N2 up to Nk are the positive integers, and we have A1, A2 up to Ak are the integers. So we need to find the value of x. This is the formula for finding the value of x. X is equal to A1 into M1 into Y1 plus A2 into M2 into Y2 and so on. And then you have to take mod M. So how to find the value of M? M is multiplication of N1 into N2 into N3 up to Nk. Then we need to find Mi and then MIY. Then I will explain how to calculate all these values. So here X is a simultaneous solution to all of the congruences. So I will explain with example. So here we are taking three congruences, but we need to give only one solution that satisfies all the three congruences. So here the example is X congruence to 1 mod 5, then X congruence to 2 mod 6, then X congruence to 3 mod 7. So first we need to find the value of A1, A2, A3 from the given congruences. So these are the A values. So here in the first congruence, we need to find A1. A1 is 1. In the second congruence, A2 is 2. In the third congruence, A3 is 3. Next, we have to find N1, N2, N3 from the given congruences. So N1 is 5, N2 is 6, N3 is 7. So after finding A1, A2 and A3 and then N1, N2, N3, we need to calculate M value, that is capital M value. What is the formula for finding capital M value? N1 into N2 into N3 and so on. But here we are having three congruences. So we are calculating M is equal to N1 into N2 into N3. Okay, what is the value? N1 is 5, N2 is 6, N3 is 7. So 5 into 6 into 7, we got 210. M value is 210. Then we need to find M1, M2, M3 because we have only three congruences. So we need to find three M values. So what is the formula for finding small m value? Mi, that is M1, M2, M3 equal to capital M divided by that corresponding n value. So for finding M1, you need to take the capital M value. That is already you found that value 210. What is N1? 5. 210 by 5 will give you 42. Next, we need to find M2. M2 equal to capital M value 210 divided by next N2 value, you got 35. Next, M3 value, M capital M divided by N3, you got 30. So, we found A1, A2, A3, N1, N2, N3. Then, we found M value, that is we calculated from N1, N2, N3 and then we calculated M1, small m1, m2, m3. Next, we find y1, y2, y3 value. Okay. So how to find y1, y2, y3 value? This is the formula. Mi into ya equal to 1 mod ni. Mi into ya equal to 1 mod ni. Already we got this value m1, that is 42. But we don't know the value of y1. We need to calculate by using this formula. So 42 into y1 equal to 1 mod 5. So we need to take 42 mod 5. So first we need to take 42 mod 5. 42 mod 5 is what? Mod always will give you the remainder. So 42 mod 5 will give you 2. So you have to substitute the remainder value in this place. Instead of 42, you need to substitute the value 2. So 2 into y1 equal to 1 mod 5. So you have to find the value of y1, but we don't know the value of y1. But whatever may be the value of y1, it should be multiplied with 2, but you have to take mod 5, then it will give you 1. So first we have to find in the trial and error method. So first you put 1, 2 into 1, if you take mod 5 will give you 2, but we need 1. Okay, then if you put 2 here, 2 into 2, 4, 4 mod 5 is what? 4. But we need 1. Okay. Then next you put 3. 3 into 2, 6. 6 mod 5 is what? 1. So we got the value 1. So what is the correct value of y1? 3. Because 2 into 3, 6. If you take mod 5, 6 mod 5 is what? 1. The remainder is 1. So we got 1 here. So what is the correct value of y1? That is 3. Next, we need to find the value of y2. How will you find the value of y2? Use the same formula. m2 into y2 equal to 1 mod 6. That is n2. So first you take 35 mod 6. 35 mod 6, what is the remainder? 5. Then you substitute the value 5 here. So 5 into y2 equal to 1 mod 6. 5 into y2 equal to 1 mod 6. Similar way, you can find the value of y2. So if you put 1, you cannot get the value of 1. If you put 2, you cannot get the value of 1. So if you substitute 5, 5 into 5, 25. 25 mod 6 is what? 5. Okay, so 25 mod 6 is 1. So the y2 value is 5. 25 mod 6 is what? 1. So you get the value 5. So y2 value is 5. Similarly, you can find the value of y3. So y3 is equal to 4. We found all the y values. y1 is 3, y2 is 5, y3 is equal to 4. Next, we have the formula x is equal to a1 into m1 into y1 plus a2 into m2 into y2 plus a3 into m3 into y3, then mod m. So here we are having only 3 congruences. That's why we are taking only 3 addition values. If you are having n number, for example, if you are having 4 or 5 congruences, then you can add a4 into m4 into y4 plus a5 into m5 into y5 and so on. Okay. Since you are having only 3 congruences, I am adding only the three terms. Okay. So what are the values? A1 is 1 here. M1 already we got the value 42. Y1 we have calculated 3. Substitute all the values here. Then plus. Then substitute the values for the second term. Plus substitute all the values for the third term. Okay. Then you take mod capital M value. Already we have calculated capital M value. N1 into N2 into N3 we got 210. Okay, substitute the value capital M value 210. Okay, we got 836 mod 210. So what is the value of 836 mod 210? 206. So our calculation part is over, but we need to check whether this 206, that is x value, satisfying all the congruences or not. We need to check. So this is the verification part. So what is the congruence? X congruence 1 mod 5, X congruence 2 mod 6, X congruence 3 mod 7. So in the place of X, you substitute 206. First 206 congruence 1 mod 5. So how will you ensure the congruence? What is the formula? If A congruence to B mod n, if you are saying A congruence to B mod n, then A minus B is a multiple of n. This is the formula for ensuring the congruence. So here 206 minus 1 equal to 205. 205 is what? 205 is a multiple of this n value. So here 206 satisfies this congruence 1 mod 5. Okay, come to the second congruence. Substitute the x value 206 congruence to 2 mod 6. This is my second congruence. So how will you check as per the formula of congruence? 206 minus 2 will give you 204. This is the multiple of 6. Okay, so this x value 206 also satisfies the congruence, second congruence. Come to the third one. 206 congruence 3 mod 7. So 206 minus 3 will give you 203 is a multiple of 7. Okay, so all the three values will be satisfied with the x value. That is 206 satisfies all the three congruences. So x value, this is a single x value solves the simultaneous congruences. This is the beauty of Chinese remainder theorem. Okay, I will give you the second problem for you. A bag has contained a number of pens. If you take out 3 pens at a time, 2 pens are left. If you take out 4 pens at a time, 1 pen is left. And if you take out 5 pens at a time, 3 pens are left in the bag. What is the number of pens in the bag? So here first we need to write the congruences. Okay, write the congruences, then solve the congruences in the similar way. Okay, so how to write the congruences? In the first sentence, if you take out 3 pens at a time, 2 pens are left. So the left out thing is the first one and the mod value is the take out thing. Okay, so yes, congruence 2 mod 3. So in the second case, 4 pens at a time, 1 pen is left. Okay, so if you take out 4 pens at a time and 1 pen is left. So how will you write x congruence, the left out thing, that is 1 mod the take out things 4. Okay, so x congruence 1 mod 4. What is the third one? Similarly, you have to write the third one, x congruence to 3 mod 5. After writing these congruences, you can solve this problem in the similar way of problem 1. Okay, everyone understood this thing. So this is the beauty of Chinese remainder theorem. Next we will move to extended Euclidean algorithm. Already you have studied about symmetric encryption and asymmetric encryption. Okay, so you have studied about polyalphabetic and monoalphabetic. If you take monoalphabetic encryption, you have 3 important types of monoalphabetic ciphers. One is additive cipher, multiplicative cipher, and affine cipher. Okay, if you take additive cipher, we have encryption process and decryption process. Additive cipher, in the case of encryption, you just add all those things, right? So in the case of decryption, you subtract the things. That is the process of additive cipher. Come to the second type, multiplicative cipher. In the case of encryption, you just multiply the value and get the ciphertext. And in the case of decryption, you have to divide and get the plain text, right? So here you have to divide, and it is multiplication inverse, multiplicative inverse. If you are going to divide it by 5, that is 5 inverse. If you are going to divide it by 6, that is 6 inverse, or 5 inverse mod 26, 6 inverse mod 26. It is somewhat difficult to find the multiplicative inverse. So we have this extended Euclidean algorithm for finding multiplicative inverse. For finding multiplicative inverse, you have some value, for example 4 into 1 by 5 mod 26. How will you write 1 by 5 mod 26? That is 5 inverse. For finding that multiplicative inverse, we use this extended Euclidean algorithm. So if you want to solve some RSA algorithm or the calculation of RSA algorithm, surely you will find this multiplicative inverse. So you have to use this extended Euclidean algorithm for finding the multiplicative inverse. First I will explain the algorithm, then we will see the example. So extended Euclidean algorithm has 2 variables, important variables, m comma b. Okay, what I told you, 5 inverse mod 26, that value 5 and value 26. These are the 2 variables here. So here we are going to use three variables A1, A2, A3. Already they have given the values for A1 and A2. So A1 is 1, A2 is 0 and A3 M value. You have to substitute 1 for A1 and 0 for A2 and M value for A3. And similarly we have B1, B2, B3. Already they have given two values B1 and B2 and we substitute the value of B in the place of B3. Next, we need to check the B3 value. We need to put the tabular column and we have to do some calculation. Based on the calculation, we find this B3, B2 values. Okay. So if B3 equal to 0, then return A3 equal to GCD of M comma B. That is, it means that there is no inverse, no multiplicative inverse. As it is, we are getting the values. If we next step is we need to check the B3 value. If B3 is 1, then you have to take the B2 value. This B2 value will give the answer or the solution for this B inverse mod M. What is B inverse mod M? I gave you the example 5 inverse mod 26. If B3 is 1, then you need to take the value of B2. That will give you the solution for the multiplicative inverse. This is the procedure. Okay. So first we have to find the quotient. Quotient is what? Already we have the value of A3 and B3. A3 divided by B3. Not mod, this is division. Okay. Next for T1, T2, T3, we need to calculate this T1, T2, T3. For T1, it is the formula A1 minus this quotient. Q is quotient. A1 minus QB1. For T2, this is the formula A2 minus QB2. T3, A3 minus QB3. Then for A1, A2, A3, we need to substitute B1, B2, B3. For B1, B2, B3, we need to substitute T1, T2, T3. This is the algorithm. I will then you have to continue this process. Why we want to continue this process? Till we get B3 is 1. If you got B3 1, then you can get the solution from B2. So until then you have to repeat the process. Okay. So I will give you one example. But 5 inverse mod 26 is a very simple example. That's why I have taken a very big example, 3-digit and with 4-digit example. Inverse of 550 mod, this is mod, finite field value 1759. So how will you write this value? 550 inverse 1 mod 1759. 550 inverse mod 1759. So for finding all those value or multiplicative inverse, you have to construct this tabular column. You have to construct this tabular column. What are the variables? Q, that is quotient, then A1, A2, A3, then B1, B2, B3. First, we need to fill the first row. In the first row, what is the quotient? We didn't fill the first row value. That is quotient. How will you calculate the quotient? A3 divided by B3. But here we don't have any value. Before finding this quotient value, we don't have any A3 and B3. Simply you put dash. Okay. Then you start filling the values of A1, A2, A3. A1, A2 already I told you know, A1 and A2 already these values are given in the algorithm 1, 0. A3 value is what? Your 1759 M value. Then B2, B1, B2, B3. B1, B2 already given in the algorithm 0, 1. Then B value. B value is what? That your inverse value, 550 inverse. Substitute all the values. I repeat, for the quotient value, for the first row, we don't have A3 and B3 value. So simply you put dash. A1, A2, A3, A1, A2, you can take it from the algorithm that is already given 1 and 0. A3 is what? M value 1759, this value. So B1 and B2 are given in the algorithm 0 and 1. So B3 is inverse value, B value 550. After substituting the first row, you have to check the B3 value, because if you got 1 in B3, then you got the solution, right? So you have to after completing each and every row, you need to check the B3 value. If you find 1 in B3, then this is the solution. Whatever may be the value in B3, that is the inverse, multiplicative inverse. So here what is the value? This is 550. Okay, so you have to continue the process. Come to the second row. Second row, what is the Q value? You have to refer the first row for finding the quotient value. Refer A3 and B3 available in the first row. So A3 divided by B3 will give you the quotient value here. Then what is the second row value of A1, A2, A3? You just copy the previous row values, that is the values of B1, B2, B3. That is the algorithm. So you just copy the values of B1, B2, B3. That is, you substitute B1, B2 values, B3 values in the place of A1, A2, A3. So you just copy the previous row values of B1, B2, B3 in the place of A1, A2, A3. Then come to B1, B2, B3. So how will you find B1, B2, B3? That is the value of T1, T2, T3. So for B1, T1 value, for B2, T2 value, for B3, T3 value. How will you find T1, T2, T3? T1 is the formula A1 minus QB1. What is T2? A2 minus QB2. What is T3? A3 minus QB3. So for B1, you have to find T1, A1 minus QB1. So you have to take the values from the previous row. So A1 is 1 minus, what is the Q value? You have to take the Q value from the current row. So that is 3, and then B1 value. B1 value is 0. So for A1 and B1, you have to refer the previous row. For Q value alone, you have to take it from the current row. Okay, so A1 is 1 minus 3 into 0. 3 into 0 is 0, so that is 1. So the value is 1. Similarly, you can find the value of T2 with the help of A2 minus QB2, and similarly you can find the value of B3 with the help of A3 minus QB3. After completing this row, what I told you, you have to check the B3 value. If it is 1, that's all. You got the solution in B2. But here, what is the value? 109. So you have to repeat the process. How will you repeat? So quotient, you refer the previous row value. So A3 550 divided by B3 109, you got 5. So you copy the values of B1, B2, B3. That is, you substitute the values of B1, B2, B3 in the place of A1, A2, A3. So for B1, B2, B3, what you have to do? You calculate T1, T2, T3 with the available formula. Okay, after completing the third row, you need to check the value of B3. Whether it is 1, no, it is 5. Again, you have to continue the process. You see the fourth row, again you got the value 4, not 1. So you continue the process. So in the fifth row, you got 1 in B3. You got 1 in B3. If B3 is 1, then you can take the value of B2. What is the value of B2? 355. 355 is the solution of 550 inverse mod 1759. Okay, since it is a very big number, that is the 3-digit number along with the 4-digit number, that's why it takes some 5 rows or 5 iterations to complete the process. If you are solving 5 inverse mod 26 within 2 steps, you will get the answer. The second step itself, you find 1 in B3, then you can take the value of B2, that is your solution, multiplicative inverse. Okay, so since it is a 3-digit, 4-digit number, so the process is going on. We take some 5 iterations to get the value 1 in B3. So if you got 1 in B3, this B2 will give you the solution. That is the multiplicative inverse of 550 inverse mod 1759. Okay, so once you understand the process, then you can use this extended Euclidean algorithm for solving RSA algorithm or any multiplicative ciphers. Okay, that's all about extended Euclidean algorithm. Then we'll move to the very interesting part, public key crypto systems. Okay, so we are going to see some principles of public key crypto systems. So already I studied about the building blocks of encryption techniques. What are the two building blocks of encryption techniques? Symmetric and asymmetric. Okay, symmetric we have monoalphabetic and polyalphabetic. Okay, asymmetric you have a lot of algorithms. So monoalphabetic you have additive and multiplicative and affine cipher. So this is about monoalphabetic. And polyalphabetic you have some one-time pad, Vigener cipher. Okay, so n number of algorithms in polyalphabetic. If you take asymmetric, we have some substitution ciphers and transposition ciphers. Okay, so this asymmetric encryption come under the category of public key crypto system. Okay, so we have the concept of using single key and multiple keys. So if you take symmetric key encryption, you are using a single key that should be shared with the recipient. Okay, so if you talk about the asymmetric encryption or the public key crypto system, you have to use the pair of keys. You have to use the pair of keys. Pair of keys means what? One is called private key, the another one is called public key. Okay, so here the symmetric algorithm uses one key for encryption and another key for decryption. What we have to do? Either we have two entities, right? Sender and the receiver. Either sender or receiver has to generate the pair of keys. Okay, sender has to use the private key and receiver has to use the public key. Okay, but keep it in your mind, either sender or the receiver has to generate the pair of keys. Why? Because these keys are mathematically related. So one entity or one person has to generate the pair of keys. One key will be used for encryption. If suppose private key is used for encryption and the other key, public key, is used for decryption. Okay, so here we are having some security services. Already you have studied about security services. What are the important security services? Confidentiality, authentication, availability, access control, and non-repudiation. These are the primary security services. But here we are going to see the important important services is confidentiality and authentication, because we are going to use these two services in this public key crypto system. First we are going to see confidentiality. So the importance of confidentiality. So already I told we have two entities. Here I am mentioning source and destination. We call it as sender and receiver. So source is A and the destination is B. So we need to use some encryption algorithm along with the key for completing the encryption process. And at the same time, receiver side, we need to use the decryption algorithm along with the key. If it is a symmetric encryption, you have to use the same key. It should be shared among the users. If it is a asymmetric encryption, you have to use the other key. That is, if it is a private used by the sender, you have to use the public, and vice versa. So here you see the source, they are generating the message, then X is the original message. So we are using the encryption algorithm. So here they are using the public key. So if you want to maintain the confidentiality, then no one should open the message. No one should open the message. Only the intended recipient has to open the message. So it should be opened by the private key. If you are using the private key here, then anyone can, any authenticated recipient can open the message or can read the message by using the public key, which is available in the public directory. So if you want to maintain the confidentiality, that is secrecy, only the intended recipient should open the message, should read the message. Then the sender has to use the public key, the receiver has to use the private key. So sender is using the public key for encryption. Here we are having in the middle part, we have the crypt analyst. If they take the message and they'll do some process and try to get the original message. So here the receiver received the message. So here they are doing the decryption part, decryption using the decryption algorithm along with the private key. So if you give this setup, only the intended recipient can open the message or read the message using the private key. This exists here. It exists confidentiality. Okay. Then what about the authentication? Authentication is a user ID. So you are having your own college ID for to enter into your class or your college. Okay. So here that shows the authentication, that ensures the authentication. It's like signature. It's like your key. It's like your private key. So here we are having the same setup. Sender and the receiver, or source and destination. So sender is generating a message using the encryption algorithm. They want to encrypt, but here confidentiality is not important. Only thing is the authentication of the sender. Authentication of the sender. Suppose if you are receiving some important circular from your principal or from authenticated person, so at the end of the page we need to check the sign of your principal, right? Then the message is authenticated. Here also the same thing. It should be authenticated by the sender. Authenticated sender. Then what? Then the sender has to use the private key. Private key is like his or her signature. So the receiver B, destination B, receives the message, but here we are not bothering about the confidentiality. Any authenticated person can see the message. So circular is what? Sent to all, right? Sent to the all. So anyone can read the circular. So here we are not bothering about the confidentiality. Only thing is authentication. So if the sender is using the private key, then the receiver has to use the public key for decryption. So this setup ensures authentication because the sender is releasing the message with his or her own signature, that is identity, authentication. So this message is authorized, authenticated message, authenticated user. Sender is the authenticated user. Okay. So then come to RSA algorithm. This is the very famous public key crypto system, public key algorithm. RSA, this is a best known and widely used public key scheme. This was developed by three authors, Rivers, Shamir and Adelman of MIT in 1977. Okay, so this the beauty of RSA scheme is we have already studied about the plain text and the ciphertext. Plain text is the original message and the converted form of the original message is called ciphertext. Okay, we are doing n number of processes, that is called encryption for converting the cipher plain text to ciphertext, and we are doing a number of processes, that is called decryption for getting the plain text or the original message. Okay, come to RSA algorithm. Here the plain text and the ciphertext are integers. We have studied about the Caesar cipher and other polyalphabetic, monoalphabetic ciphers. There we are using some alphabets, right? But if you are using alphabets, then the attacks, brute force attack is possible. What do you mean by brute force attack? Trying all the possible key values, because we are having only 26 alphabets. So if you take trial and error method, you can try all the possible 26 alphabets you can find in one way. Okay, so here we are using integers between 0 and n minus 1. Normally we take n integers, we start with 0, so that's why it is 0 to n minus 1 for same n. So the typical size for n is 1024 bits. Normally in cryptography, we are representing all the plain text and the ciphertext in terms of bits. Sometimes if it is a block cipher, then we have to represent those plain text and the ciphertext in blocks. Okay. So here we need to take 1024. This is the size of n, 1024 bits. Encryption is denoted by E and decryption is denoted by D. Plain text is denoted M. Okay. So ciphertext is denoted by C. Sometimes we are using X and Y value, but here the plain text is denoted by M and the ciphertext is denoted by C. Okay. Come to the ingredients of RSA. Okay, so here this is a public key crypto system, I told you, So we are having two keys. This is asymmetric encryption, and the other name for asymmetric encryption is public key crypto system. We are using two keys, public key and private key. So what is public key? So public key is referred as PU. Okay, So both are starts from P, the letter P. That's why it is differentiated from private key. So here we are using PU. For private key, we are using PR. So here we are having the variables E and N. Those values contributes to the public key. And we have D, N. Those contributes to the private key. Okay. So both the sender and the receiver must know the value of N. Okay. And sender knows the value of E and receiver knows the value of D. Okay. So here next part is key generation. We have two prime numbers. We need to select two prime numbers because it is we have a very limited number of prime numbers. That's why they are taking prime numbers. It's for the hackers to it's a time consuming for the hackers to find the ciphertext or to find the key value or the plain text. That's why they are taking prime numbers along with the exponentiation. Okay. So here the condition is we need to take the prime numbers P and Q value, but the condition is P is not equal to Q. Okay. Then we need to calculate N value. What is N? P into Q will give you N. Okay. Next we have to calculate pi of N. What is pi of N? Euler's torsion function. Pi of N is Euler's torsion function. Normally the formula for pi of N is N minus 1. But here what is N? P into Q. We have two variables. So here pi of N is P minus 1 into Q minus 1. Understand the concept? What is pi of N? Pi of N is N minus 1. Generally the formula for Euler's torsion function. Pi of N is Euler's torsion function. Pi of N is equal to N minus 1. But what is N here? P into Q. We are taking two prime numbers. So it is P minus 1 into Q minus 1. Okay. So next thing is we need to take or we need to select E value. So here some values are selected, some values are calculated. Okay. So E is relatively prime to pi of N and it should be less than pi of N. You have a freedom to select the E value, but with some constraints. That is, it is relatively prime to pi of N and it should be less than pi of N. Then after selecting E value, you can calculate D value. You can calculate D value because E is public, but D is not public. That's why we are calculating. All the public values, you can select the values. Those are public values. If you are calculating something, those are called private values. This is a simple concept you need to understand. So you have to calculate D value. What is the formula or what is the solution for finding the D value? DE congruence to 1 mod f of n or 1 mod pi of n. Okay, so with the help of this formula, we can calculate the D value. I will explain with the example. Okay, after completing the key generation part, we come to the encryption and decryption part. Okay, so what is encryption? Plain text is converted to ciphertext. That is, original message is converted to the coded form, converted to the coded form. So here M is the original message. The condition is M should be less than N. Okay, because here we are playing with integers, right? So all the variables are having integers value. So here M is less than N. So how to find the ciphertext? Ciphertext is represented as C. So C equal to M, that is your original message, that is plain text, to the power E. What is E? Small e is your public key value and mod N value. So modulus value. Then come to the decryption part. You need to get the plain text. You receive the ciphertext. From that you have to calculate your plain text. What is the formula? Plain text is M equal to C to the power D mod N. What is C? Ciphertext. The receiver received the ciphertext. And what is D? That is private key value. That is private key value mod N value. This is the ingredients of RSA. So you should understand the public key and the private key and how to calculate the key value and what is the formula for encryption and what is the formula for decryption. Okay, then come to the example. So here, for exam point of view, they have given the P and Q value. Sometimes they have given E value also. Otherwise, you have to select the E value. Based on these values, you can calculate D value and find the encryption C value and then decryption M value. Okay, so P and Q values are given. Both are prime numbers. Keep it in your mind, both are prime numbers. So here P value is 3, this is a prime number. Q value is 11, this is also a prime number. But the condition is what? P is not equal to Q. Okay, so 3 is not equal to 11. Okay, what is the next step? Compute N value. What is the formula for N? N is equal to P into Q. So 3 into 11, 33. Next you have to calculate pi of N. What is pi of N? Euler's torsion function. The formula is N minus 1, but here P minus 1 into Q minus 1. What is P? 3. So here it is 2. What is Q? 11. So here it is 10. 2 into 10, 20. You got pi of N value 20. Okay. Next is you have to choose or select E value. So E is relatively prime to pi of N and it should be less than pi of N. But here pi of N is 20, then obviously E should be less than 20. But here we selected E is equal to 7. It should be a prime number. Okay. Then with the help of E and pi of N values, we are going to calculate the value D. Okay, so what is the formula? ED congruence to 1 mod pi of N. What is the meaning? How to calculate the value of D? So a simple way is E into D take mod, then it should give the value 1. That is the GCD value. Okay, so multiply E value and you can take any D value. It should be multiplied with the E value and you take mod value. Mod is what? Pi of N. Mod 20, it should give 1. Okay, so already we have the E value 7. So if you put 1 here, 1 into 7, 7 mod 20 is what? 7. Okay, leave it. You take D value 2. 2 into 7 is 14. 14 mod 20 is 14. So we cannot get 1. So if I substitute 3, so it is a trial and error method. Simple way for finding this D value is trial and error method. So if you put 3 into 7, 21. 21 mod 20 is what? 1. So we can take the D value 3. So you may ask, if you find 1 for n number of values of D, yes, of course, you can take any value of D. Okay, so if you get 1, then you can take any value of D. Okay, so here the public key is E comma N because E is selected and D is calculated. So E comma N will give you the public key 7 comma 33 and the private key is D comma N. D is calculated by using this formula 3 comma 33. Okay, so once you generate the key values, then you can go for encryption process. What is the formula for doing encryption? C, ciphertext. We need to calculate ciphertext. Ciphertext equal to M to the power E mod N. What is M? M is given in your exam. Then M is equal to 2. 2 to the power 7 mod 33 will give you 29. You can do it in your, you can calculate mod value by using your calculator. Okay. Then decryption, M is equal to C to the power D mod N. C is what? Already we got the ciphertext value 29. 29 to the power 3. That is your D value. If you take mod 33, you will get the value 2. Okay. So this M value matches with this M value. So this encryption and decryption process are correct. Okay. So we got the correct result. It means the receiver got the original plain text. Okay, so here the beauty of RSA algorithm is we are using prime numbers and we are using exponentiation. So if you are using prime numbers and exponentiation, it is a time-taking process or time-consuming process for hackers. So that's why they used this prime numbers concept and exponentiation concept in RSA algorithm. It's a very powerful algorithm for public key crypto system. Okay, so we'll see a few more examples using RSA. The first example, in a public key system using RSA, you intercept the ciphertext C equal to 10 sent to a user whose public key is public key E equal to 5, N equal to 35. What is the plain text M? So in this question, they have given the ciphertext value. What are the ingredients we need? We need M. We need C. We are selecting this E value and N value and D value. So in this example, they have given this C value, E value, N value, and they are asking M value plain text. So here you see the formula. What is M? M is equal to C to the power D mod N. So here C value is given, but what about the D value? We don't know the D value, but N value is given. Okay, so but here they have given E value. With the help of E value, we can find D value, because ED congruence to 1 mod pi of n. But we don't know the value of pi of n, right? But we have the value n. With the help of n, we can calculate pi of n. What is the formula for pi of n? P minus 1 into Q minus 1, right? So if you know the value of P and Q, then only you can calculate the value of pi of n. Okay, so here n is equal to 35. So trial and error method, we can find the value of P and Q. It should be prime. What is the condition for selecting P and Q? P and Q are prime numbers and P is not equal to Q. So 35, if you factorize this n value, you can get 7 and 5. Whether 7 and 5 are prime numbers? Yes, 7 and 5 are prime numbers. They are not equal. So 7 into 5, 35. So 1 will be your P value and the next value is the Q value. Then with the help of P and Q value, you can calculate n. Already you have the n value, you can calculate pi of n. What is pi of n? Pi of n equal to P minus 1 into Q minus 1. So 7 minus 1 is 6, 5 minus 1 is 4, 6 into 4, 24. You got the value pi of n 24. Why we are calculating pi of n? We need to calculate D value because E into D congruence to 1 mod pi of n. So we need pi of n value. Okay. So here E into, here the question mark is D value equal to 1 mod pi of n. Okay. So what is your E value? E value is 5. If you put 1 into 5, 5. 5 mod 24 is 5. We cannot get 1 here. So if you substitute 2 into 5, 10. 10 mod 24 is what? 10. We cannot get 1 here. And substitute 3, we cannot get 1. So if you substitute 5, then 5 into 5, 25. 25 mod 24 is 1. Okay. So here the correct value or the apt value is 5. So here D value is 5. E value is 5. D value is also 5 because 5 into 5, 25. 25 mod, how will you get this 24? That is my pi of n. So 25 mod 24 will give you 1. We need to check always this GCD value for finding the D value. Okay, so you got the D value. What is the formula for finding M value? M is what? C to the power D mod N. C to the power D mod N. What is your C? 10. What is your D? 5. 10 to the power 5 mod N 35. So you have some reminders 2857. You have quotient 2857 and the remainder 5. Remainder 5. That is your M value. Okay. Similarly, if you face this problem, that is the C is given, E is given, N is given, and they ask you to find M. First, see the formula for finding M. It has D. So for finding D, we need pi of n. For finding pi of n, we need P and Q value. So similarly, trial and error method, you can find P and Q value. With the help of P and Q value, you can calculate pi of n. After calculating pi of n, you can find the value of D. After calculating D, you can get the value of M. Okay. So this is the simple way of finding the value. Come to this next example. In an RSA system, the public key of a given user, that is the public value, E is 31 and N is 3599. What is the private key of this user? So they are giving hint value. Use trial and error method. I told you in the previous example. So trial and error to determine P and Q. Then use the extended Euclidean algorithm to find the multiplicative inverse of 31 mod pi of n. Okay. So here trial and error method. So we have to put some values for P and some values for Q. Then you multiply both the values. At one point of time, you can get some values. But keep it in your mind, both values are prime numbers and P is not equal to Q. That condition should be satisfied. Then you can find the P and Q value by trial and error method. You can put any value. So here for finding D value, I'm putting 1, 2, 3. Then at last I'm finding 5. Okay. So similarly, you can substitute some values for P and Q, but it should be a prime number for P and Q, and P is not equal to Q. In this way, you can find the P and Q value, and then after finding P and Q value, you can find pi of n. But what the next question? Use the extended Euclidean algorithm to find the multiplicative inverse. What is multiplicative inverse? 31 inverse mod 3599. So 31 inverse mod 3599. So how will you find? I told you about the extended Euclidean algorithm. So you write or put it in the tabular column, write the quotient A1, A2, A3, B1, B2, B3. So in the first row, you don't find Q value, but A1, A2 already available in the algorithm. A3, you can give the value of M, and that is 3599. And for B value, that is 31. In this way, you can find the multiplicative inverse of 31 inverse mod 3599. Okay. Next, third problem is, suppose we have a set of blocks. Okay, set of blocks encoded, that is encrypted with the RSA algorithm. Block by block, we are going to encrypt the plain text by using RSA algorithm. That is the meaning of the sentence. And we don't have the private key. Okay, assume n is equal to pq. Always n is equal to p into q. E is the public key. We know that E is the public key. Suppose also someone tells they know one of the plain text blocks as a common factor with n. Does this help us in any way? Yes, we don't have a private key. Okay, we don't know the plain text and we don't know the ciphertext, so we cannot calculate the pi of n value. And but one of the member is telling that the plain text blocks has a common factor with n. So they know the one of the plain text blocks. So here we are taking factorization. Already you have studied about that. So does this help us in any way? Yes, if a plain text block has a common factor with n mod n. Okay, so then the encoded block will also have a common factor with n mod n. So with the common factor, but it is smaller than pq. So it must be a factor of p or q. Okay, so the plain text blocks must be a multiple of p or q. So we can test the primality. Already we have the Miller-Robin test, and we study about the primality test. Okay, so we can do the test for prime numbers. If it is prime, it is p or q. So in this case, we divide into n to find the other factor. Once you find the one prime number, we can take the other prime number. If it is not the prime number, simply you do the factorization and get the value. So this is the explanation or answer for this question. In the RSA public key encryption scheme, each user has a public key E. Okay, then the private key D. Suppose Bob leaks his private key. Private key is very important. It should not be leaked, but Bob leaks his private key. Then rather than generating a new mod, that is new mod pi of n, he decides to generate a new public and a new private key. Is this safe? It is not safe. Why? Because once Bob leaks this private key, then the other person, other entity, Alice, use this factor mod n, and you crack any message that Bob sends. Once Bob leaks his private key, this Alice uses this private key for finding the value. So this is not safe. What is the solution for that? They have to change the n value, that is, so that the pi of n value will be changed, then it is safe. Otherwise, it is not safe. Come to the next problem. Suppose Bob uses the RSA crypto system with a very large modulus. Normally, we are seeing a very small mod numbers, 5, 7, 11, and so on. But here, they are using very large modulus n, for which the factorization cannot be found in a reasonable amount of time. It is a time-consuming process. That's why they are using prime numbers with exponentiation. Okay, so this is for the hackers to take a reasonable amount of time to find the ciphertext or plain text value. So suppose Alice sends a message to Bob by representing each alphabetic character as an integer between 0 and 25, and then encrypting each number separately using RSA with large E and large N. Is this method secure? If not, describe the most efficient attack against this encryption method. Here, what is the core concept of this problem? They are using alphabetic characters. How many alphabetic characters we have? Only 26. So they are using 0 to, already I studied about the numerical values for the corresponding alphabets, right? For A, we have 0, for B, 1, like that, and we have 25 for Z. Okay, so only we have 26 alphabets, and we have the numerical values from 0 to 25. So here they are giving the essence that they are using only 0 to 25, only 26 alphabets are using. In the integer part or the numerical part, they are using only 0 to 25, very less numbers or very less values are using. So here the attack is possible. They are asking, is this method secure? No, this is not secure. Why? Because they are using only 26 alphabets, 0 to 25 values. It is very easy. You are having only 26 alphabets or 25 values, 26 values, 0 to 25. Then we can have a attack. That is the lookup table method. You can write all the possible ways, and then at one point of time you can get the match of plain text with the ciphertext. That is called lookup table. So one by one, if you are writing the corresponding values at one point of time, you can get the corresponding ciphertext value for the plain text or the plain text for the ciphertext. So here attack is possible. This method is not secure because they are using alphabetic characters. Only 26 values can be used here. So the attack is possible. They use the lookup table for finding the corresponding ciphertext. So this method is not secure. That's why we are using 3-digit, 4-digit prime numbers and exponentiation. That is very secure. So if you are using prime numbers with exponentiation, it is a time-consuming process. It takes time for the hackers to get the corresponding plain text for the ciphertext. Okay. That's all about RSA algorithm and its problems. Then we'll move to Diffie-Hellman key exchange algorithm. So this is a different algorithm. Okay. So this is not a encryption algorithm. This is a key exchange algorithm. Why it is called key exchange algorithm? I told you about symmetric and asymmetric encryption. Okay. So symmetric encryption, they are using only a single key that should be shared with the shared by the users, senders and the receivers. Okay. But if you are using a single key, that key should be shared with the other entity. So what is the best way to share? Use some sort of techniques or algorithm. So they found Diffie-Hellman key exchange algorithm. Okay, so they are exchanging the key using mathematics, right? So mathematical way of exchanging the key, that is secure. Okay, so here we are taking the famous entities Alice and Bob, right? So Alice and Bob share a prime number q, okay, and an integer alpha. So this Diffie-Hellman, the base for the Diffie-Hellman is discrete logarithm. Okay, so discrete logarithm, we have some primitive root. We need to find the primitive root. So those concepts, discrete logarithm and primitive root concepts used in Diffie-Hellman algorithm. It's a pure mathematics. So Alice and Bob share a prime number q and an integer alpha, and alpha should be less than q, and alpha is the primitive root of q. Okay, so this is common for Alice and Bob. Okay, come to the left side. Alice generates a private key that is represented as XA. Why it is represented as XA? Because both the sides we are using X for private key. If it is generated by Alice, then it is represented as XA. If it is generated by Bob, then XB. Okay, this XA less than, it should be less than Q. What is Q? Q is the prime number. So here Bob generates this private key XB and it should be less than Q. They can generate their own private key, but the condition is it should be less than Q. Then they are calculating the public key. So the Y is the common representation for public key. So if Alice generates the public key, that is represented as YA. If Bob calculates the public key, then it is represented as YB. That is the difference. So YA is equal to alpha to the power XA mod Q, X suffix A. Okay, you have to write like that. And YB equal to alpha to the power XB mod Q. That is generated, public key generated by Bob. Okay. After selecting the private key, after calculating the public key, they want to exchange. Okay. So here they have to, initially they have to exchange the public key. So this public key YB is shared with Alice, and then this public key YA is shared with Bob. Okay. Then they are going to calculate the secret key K. Both of them are calculating the secret key K. K is equal to YB to the power XA mod Q. This side, Bob is also calculating the secret key, and K equal to YA to the power XB mod Q. Okay, so this is the algorithm. So user A and B wish to exchange a key. So this diffie-Hellman is the purpose for exchanging the key. So A selects the random integer xk, xa less than q, ya, and they are calculating ya alpha to the power xa mod q. So then they are calculating k value. Then we are going to see the magic, how they are going to exchange the value. Once you see the algorithm, after completing the process, at the end of the algorithm, you see the magic, the key was exchanged. Okay. So first you take the k value, any one of the k value. So here we have two k values. You can take any k value. So here I'm taking the a k value. That is Alice k value. K equal to YB, Y suffix B to the power X suffix A mod Q. Okay. So here, this is YB is what? Public key generated by Bob. So you can, you know the value, right? You can substitute it here. So what is YB value? Alpha to the power XB mod Q. And then here we have the power, right? XA mod Q. Okay. So with the modular arithmetic concept, this is modular arithmetic concept, we can take a mod outside. So alpha to the power XB to the power XA mod Q. So here we can multiply the powers alpha to the power xb into xa, simply removing the brackets. So alpha to the power xa and into xb into xa mod q. Okay. Then using the powers, so alpha to the power xa, xb, this can be written as alpha to the power xa into xb mod q. So if you put the bracket, then alpha to the power xa to the power xb mod q. So again, the way of modular arithmetic, concept of modular arithmetic, you can add the mod on both sides, that is alpha to the power xa mod q to the power xb, then mod q. So what is alpha to the power xa mod q? That is the public key of A, user A. Then you can substitute ya, y suffix A, ya to the power xb mod q. Ya to the power xb mod q is what? That is the secret key of user B. Now B got the secret key from A. Now you can see the beauty. The keys are exchanged. Actually, they have calculated the secret key separately. A has calculated the secret key separately, and B, Bob, has calculated the secret key separately. But once you follow this algorithm, what is the magic here? The key has been exchanged. Okay, so this is the algorithm. We have only few lines. So the example, numerical example, the prime number q, that is 353, alpha value 3. So we need to calculate, we need to select the private key for both the users, and we need to calculate public key for both the users, and then we need to calculate the secret key k value for both the users. Then you see whether both the key values are same. If both the key values are same, then your process is over. The key has been exchanged. So prime number q equal to 353, alpha value, the primitive root is 3, a private key selected by a 97, b private key is 233, then a calculate public key ya, that is alpha to the power xa mod this q value, you got 40, and then b calculate the public key yb, that is 3 to the power 233 mod value, that is mod q value, got 248. Okay, so both are calculating the key values. So 248 here, first we calculate for Alice, that is a user a, 248 to the power 97 mod 353, we got 160. Then we calculate the k value for b, ya to the power xb, substitute all the values, that is ya value, xb value, and the q value. Then you got the value 160. Okay, both the values are same. So Alice and Bob have exchanged their keys in a very secure manner. That is with the help of Diffie-Hellman key algorithm. Okay, that's all about key exchange algorithm, Diffie-Hellman. Then come to the important part, the hash function. The first part of our session is over, public key crypto system. Then the second part is hash function. So what is the importance of hash function? So already we have studied about this encryption, decryption process. Once you get the plain text, then that will be converted to a ciphertext that will be transmitted to the another entity or the receiver. Then the receiver side, they receive the ciphertext, then that will be decrypted and got the plain text. That process is over. But here the decryption is not possible. The hash function has important property called one-way property, because once you do the process of encryption and decryption, in the transmission side we have hackers, and the hackers will capture the middle part or the ciphertext, and they can get the plain text, right? So here it is not possible. Decryption is not possible, because the important property of hash function is one-way property, meaning that if I'm going to generate the message yum, so if you apply the hash function on it, you will get the hash code. Keep it in your mind. If you generate the plain text original message, and if you apply the hash function on the message, you will get a hash code or hash value. The small h, capital H is represented as hash function, and small h is hash code or hash value. So once you got the hash code value, then you cannot decrypt the hash code value and find the plain text. Okay, so if I'm going to give the hash code or hash value, then you after receiving the hash code or hash value, you cannot get the original message value. Then how the receiver will get the plain text value or the original message? There are some procedures, there are some functions of hash function. So the concept is the plain text or the original message yum, if you apply the hash function h value, you will get a hash code value. So here we are giving the variable size message yum and produces fixed size hash code value. So we have n number of hash algorithm. You have studied about MD5, SHA-1, SHA-252. So n number of hash algorithms are there. So first we will see the functions, basic functions of hash algorithm, and then we will see the importance of hash. So here, this is source, this is destination, that is sender and the receiver. First you take the value, original message, okay, then you apply hash function on it. So once you carefully understand the flow, then you can write on your own way. Don't memorize this diagram. Okay, so here this is the original value, or we can call it as a plain text or message. We can call it as a message. So yum, So if you apply hash function on it, you will get a hash code. Okay, so here we are sending the hash code along with the message. Once the receiver receives the hash code, he cannot do with the hash code. So we need to send a message in a secure manner. So here we are having hash code. So this double line representing the concatenation. So this hash code is concatenated with the original message, and here it will be encrypted using the key K value. K is what? Symmetric encryption, that is secret value. So it will be encrypted by using the K value. This is a complete thing. We are going to transmit this value to the receiver. What is the value? M. Apply hash function will get the hash code. It will be concatenated with the original message and encrypted with the key value. But this is symmetric encryption. This is symmetric encryption. We are going to use a single key. Okay. So the receiver side, he receives the thing. So here first, what is the last thing we are doing? So here we have done the encryption process. So here we have to do the decryption first. Okay. So always we have to do the reverse process. So decryption by using this K value. If you decrypt it, you will get what? The concatenation. That is, what are the concatenation thing? M and the hash code value. Okay. So what the receiver will do, take the message and apply hash function on it, will get some hash code value. And this is generated by the receiver, and also he received the hash code value. So both the thing will be compared. So the generated hash code is same as received hash code, then the receiver accepts the message. If it is not same, then he reject the message, ask the sender to resend or retransmit the original message, meaning that it is hacked during the transmission. So the receiver won't accept the message. He asks the sender to retransmit the message. This is the way of accepting the message, accepting the original message. They are ensuring the original message, right? So if it is same, then this is the original message. No one is hacked during transmission. So they accept the message. Otherwise, the message will be rejected by the receiver. So come to the second function of hash message. Apply hash function on it. You will get a hash code here. And then we are not concatenating it. We are going to encrypt using a single key or a secret key. Then after encryption, we are going to concatenate with the original message, and this will be sent to the receiver. Then receiver first he decrypt by using the secret key, got the message. Then here also he receives the hash code. Then generated hash code will be compared with the received hash code. Then if it is same, then they accept the message. Otherwise, it will be rejected. Here come to the third part. The third part, the difference is message, apply hash function, get the hash code. Here also same process, but the difference is here we are using secret key, that is single key, or this is symmetric encryption. But here we are using private key. KR is private, KU is public. Why we are using this suffix A? This is generated by the sender A. Assume that sender is A, receiver is B. So I told you, no, either sender or the receiver generate the pair of keys. Okay. So this is not possible. Sender can generate private and the receiver can generate public. That is not possible because both are mathematically related. That's why we ask either sender or the receiver generate the pair of keys. So here we are giving the private key. So after encryption, this will be concatenated with the message. This will be sent to the receiver. So again, this will be decrypted. They got the hash code, and here they generate the hash code. This part is generated hash code because they got the original message. They apply hash function. Here they generate the hash code. Here they receive the hash code. So they compare the thing. If it is same, they accept the message. Come to the fourth function. So here we have the message, apply hash function on it, and do the encryption using the private key, concatenate it. Again, we are encrypting the entire thing using the secret key. See how we are giving the strength of the encryption or strength of the security. So first we are using the symmetric, after that we are using asymmetric. In this function we are using both symmetric and asymmetric. First we are using asymmetric using the private key, and then symmetric using a single key. So in the receiver side, I told you, we have to do the reverse process. So first you have to decrypt by using the secret key. You got the message and the hash code. After receiving the message, you apply hash function. Here the hash code is generated. Here we have the thing. So you decrypt by using the public key. Here also receiver got the hash code. Both will be compared. If it is same, then they accept the message. Then come to the fifth function, message. But here the new thing is secret key. They are going to insert a secret key that will be concatenated with the message. After that, they are applying the hash function. The previous case, simply they are applying the hash function on message, but here it is not same. So we are adding some key value, that is secret value, with the message and apply hash function on it. And then here we got the hash code, right? So this hash code is concatenated with the message. This will be sent to the receiver. What the receiver will do, and we have to add the secret value what the sender did. So here add the secret value with the message, then apply hash function. Simply if you apply the hash function on message, we won't get the correct hash code because they added some secret value. So similarly the receiver side also we need to add the secret value, but before that the receiver should receive the secret value in a secure manner. So add the secret value, apply hash function on it, and then the generated hash code will be compared with the received hash code. If it is same, then accept the message. Come to the final last function of hash function. Then message, we add the secret value, that is concatenation. After concatenation, we apply hash function on it. Then you got the hash code here. Then hash code is concatenated with the message. Then you apply encryption by using a secret value. Then receiver side, you decrypt it. You add the secret value to the message. Apply hash function. You generate the hash code. Here we receive the hash code. If both are same, accept the message. So we studied all the hash functions, basic hash function. So with the help of these basic hash functions, they developed hash algorithms. MD5 and SHA-1 are the famous hash algorithms. In this session, we see message digest algorithm. MD5 is the version. Why it is called message digest? Because we can take the arbitrary length of a message, that is variable length of the message, as an input, but we got the output in fixed length, that is 128 bit. But here we are generating some intermediate values. So all the intermediate values are 128 bit. So finally we got one 128 bit value. That's why it is called message digest. So this is developed by Ron Rivest. So this is a very important hash algorithm. So here we have few steps to understand the MD5 algorithm. So this algorithm takes the message of arbitrary length, meaning that user can give a variable length message. There is no restriction for giving a message, but it produces the output of 128-bit message digest. Okay, so here the input is processed in 512-bit blocks. This is a block cipher. So each time we take 512-bit blocks, the size is 512. So we need to do some process for getting 128-bit message digest. So here the step 1 is append padding bit. What do you mean by append padding bit? We need to pad some values to adjust the length. So it should be congruent to 448 modulo 512. This is the condition. So length should be length congruent to 448 mod 512. So we have to pad some bits to your variable length message. You have to bring this 448 mod 512. But already if you have some 448 bit long, then no problem. Anyway, you have to pad. So you have to add 512 bits to your length, then you can do the process. This is the step 1. So this is the general diagram of message digest. So here we have a variable length message. It will be padded. So we have to bring 512 bit block. So the entire 512 bit block will be divided into 512 bit blocks. The first 512 bit block is represented as Y0, then Y1, Y2, Y3 up to and YL minus 1. Because the total length is L, we started with 0, so L minus 1. Each 512 bit is processed in this hash algorithm MD5. Initially, we take some initial vector 128 bit. After that, for the second and third 512 bit blocks, we take the previous output value. We take that is not output, that is intermediate value. For the second block, that is Y1, so that is 512. If you cross and if you are putting some numbers, that is the number of bits, that is the size. So Y1 is 512, but here the input is the previous processed value, intermediate value, 128 bit block is used. And then similarly we do the process for all the input bit blocks, all the 512 bit blocks. Finally we got 128 bit digest. We got only one 128 bit, so we are accepting all the intermediate values. So this is called a message digest. Step 2 is append length. So here we need a 64 bit representation of the length. Okay, so here we need to take the least significant bit in step 1. So if the original length is greater than 264, then we have to take the lower order 64 bit. So finally we have the L into 512 bit blocks. This will be divided into Y0, Y1 up to YL minus 1. Okay. So the step 3 is we need already I told you, we have some intermediate values of 128 bits. So we need to store all these intermediate values. Why? Because these intermediate values will be used for the next process. So we need some registers, buffers. Okay. So here 128 bit buffer will be used. Why 128 bit buffer? Because the intermediate value size is 128 bit buff 128, so we use 128 buffer to hold the intermediate and the final results of this hash algorithm. So we are using 32 bit registers. So we are taking in this algorithm, we are taking 4 registers. If you talk about SHA-1, there the process is a little bit huge, so we are taking five registers. Okay, all these values are represented in hexadecimal. So these are the initialization values, these registers. Normally we need to initialize the registers. Already you studied in microprocessor. If you're not initializing those values, it will take the garbage value. So then and there, if you are using some variables or if you are using some registers, we need to initialize those registers. So we are using hexadecimal values. This is the diagram. Okay, this indicates the process, a single bit process. So the chaining variable 128 bit block, I told some random value will be taken. This is the first, this is Y0. Okay, so here we are using some registers, 32 bit registers. Finally we got 128 bit. So here we are having some variables. I will explain you. For each stage we are using some functions. This is called primitive function. Okay, so here in the first stage we are using F, the second stage we are using G, H, I. Then they are giving some table values. The table has 64 values. In each stage we are using 16 values. In the first stage we are taking 1 to 16. In the second stage we are taking 17 to 32. We are taking 33 to 48 in the third stage. Already table is given. We are using those values, 16 values for each stage. Okay, so here we are having 16 steps. That's why we are taking 16 values from the table and we are using this primitive functions. Okay, so for after completing all these 4 stages, we need to do additive modulo. All the values will be added and we are getting this 128 bit message digest. So this represents the single 512-bit block, but we are doing n number of 512-bit blocks. We are doing the process. Step 4 is the process. So this is the important part of message digest algorithm. So we are having the primitive logical functions. I told you know FGHI. We have 4 stages. For each stage, we are using different functions. Each round takes the 512-bit block that is processed with the buffer values. Okay. In step 5, we got the output that is the single 128-bit message digest value. Okay. So initially we take the initial vector value. So this is the sum. This is the sum means we are taking the 512-bit block and the register values, and each and every round we are taking the primitive logical function value. So this is the explanation for this explanation for the notation initial value, and YQ is the last qth value of 512-bit block, and L is the block message size, and CVQ is the chaining variable processed with the qth block of the message, and RFX is round function. We have 4 rounds, right? 4 stages. For each round we are using some round function value. Okay, so we are having this FGHI, that is called round function, and primitive values. Okay, so here ABCD registers value, we are using this function value. It will be added with the A value, and it will be processed with the X of K and table value and circular left shift. Then it will be added with the B value, and this is the C value. Like that, every time we are using this compression value for renaming the registers value ABCD. Okay, every time the ABCD value is different. So ABCD, so we are having this G primitive logic function and circular shift. Sometimes 1 bit, sometimes 2 bits will be used. So what is that the round function, the primitive round function? That is different for each stage, right? I told you know. So in the first stage, F, that takes B, C, D value, B register, C register, D register value. But the process is different. Here we are using some logical function. B or this is no, and B and with C, and or next B and with D. So the logical function is different for each and every round function. Round function is different for each and every stages. This is how the MD5 works. So these are the important. Similarly, we can have n number of hash algorithms. Why hash algorithms or hash functions are very important? You heard about the current technology or the current trend blockchain. Okay, that is very important for transaction. Nowadays they are using blockchain for transaction, secure way of doing the transaction. So in the blockchain technology they are using hash function, hash algorithm. SHA-256. SHA is what? Secure hash algorithm. The 256 is bit. Okay, so SHA-256 is used in blockchain. So blockchain is the current trend or current technology for transactions. Okay, secure way of doing the transactions. Ma'am, shall I continue? So we have a few more topics. Ma'am, shall I continue? Or we can discuss
Madam,
later. Yes, ma'am. Yes, ma'am. Tell me.
yeah, I think as we planned, right, we can have a second session and we have it tomorrow morning, madam. Because
Yes,
I
ma'am.
like
Yes.
students to work out on this problems, whatever the RSA algorithms and this thing.
Chinese reminder theorem. Yes, ma'am.
Yeah, so these things I like students to work out the problems, ma'am. And
Okay, ma'am.
I'll be sharing as a tutorial problems. So meantime,
Okay,
they
ma'am.
also will work it out. Tomorrow in that classroom, they can have interactive sessions with you because this is exclusive for the 3rd years. And
Okay, ma'am.
since it's an open book test, definitely your mathematical approach will help them.
Okay, ma'am.
So
Then
I think
in the next session, I will discuss about AES and Elgamal, ma'am.
Elgamal, AES, and the problems. Let them work it out.
Okay,
If they have any doubts, it will be clear tomorrow. Okay,
Okay,
students.
ma'am.
So the purpose of this session is totally for you to understand and how to approach in the open book examination. If it is a closed book examination, you'll be asked 40% sums and 80 other 60% theoretical things. So since we are anticipating, we are doing that. Okay. We'll go for question answer session, ma'am.
Okay, ma'am. If you have any doubt, you can ask me.
Thank you, ma'am, for such a knowledgeable session. We have learned more about various algorithms like RS algorithm, Diffie-Hellman algorithm, especially public and private key encryption and decryption, and the detailed explanation on solving problems, which would really help us in our examination, ma'am. I really hope that all of my dear friends got benefited from this webinar and they have increased their knowledge and faced their exams with confidence. Thank you so much, ma'am. Knowing how to answer will help you in school. Knowing how to question will help you in life. I would like to invite Miss Anita to read the queries in the chat box. Over to you, Miss Anita.
Thank you, Ms. Janita. Thank you, ma'am, for this wonderful session. Ma'am, we have some queries from our participant. And the first question
Yes.
is, how this Chinese reminder theorem used in security purpose, ma'am?
Yes. So here we depend on mathematics, right? So why we depend on mathematics? Because mathematics will give you the complexity. We need to increase the strength of the security. So if we depend on mathematics, if you increase the complexity of the algorithm, then only your transactions or your transmission part or algorithm part will be very secure. So here the Chinese reminder theorem for finding the congruences. Okay. So if you do those things for the hackers, it will take more time to decrypt it or hack the plain text. Okay. So that's why we depend on mathematics. So most of the things we use theorems and lemmas.
Thank you, ma'am. The next
Yes.
question is, in some cases, the problem does not contain the numbers. To solve it, contain wording, ma'am. How can we solve that wording problem, ma'am?
Yes, if you have some words, then for the alphabets, we have the numerical values, right? So for each and every letter, you assign the numerical value, then you got some numerical value, and then based on the question, you can solve it.
Thank you, ma'am, for answering this.
Alphabets
Madam,
A to
I think,
Z. Yes, ma'am.
Madam, I think her point of Afrin, you can unmute and talk. I think she was asked while you were asking the Chinese limited theorem, she was telling about the problems as a statement it has come.
Yes, ma'am.
But you have explained in statements also, right? That is what you meant.
Okay.
Yes, ma'am.
You have explained afterwards, ma'am, how the statements have
Okay,
been
ma'am.
given, how to make
ma'am.
that case studies as a statement. Afrin, is it
Okay,
correct,
ma'am.
Afrin?
Yes, ma'am. Yes, ma'am.
Yeah.
Okay.
So madam has given answer for that.
Okay. So if it is a normal problem, we can take the numerical value. But if it is, you are asking about that case study problem, right? So here
Yes,
the
ma'am.
left
Yes, ma'am.
out thing will be taken as a divisor. Okay. So here the other number will be taken as a dividend. So in this way, we can consider those numbers and write the congruences.
Okay, ma'am. Thank you, ma'am.
Okay, ma'am. Welcome.
Any
Thank you,
other
ma'am, for
questions, ma'am?
answering.
Only 2 questions are there. Any other questions? You people can just unmute yourself and talk to madam. Now our students are in state of shock. How many problems madam has worked? So if that all it has come, it is worked. So it is easy. We can solve all the problems as madam has explained neatly, and you have given a lot of tutorial sessions also.
Once you
So
understand the algorithm, you can use those algorithms for your final year project. So final year, if you are taking your final year project, if you take any application, then security plays an important role. So you incorporate all those algorithms, not all those algorithms. If you want, you can take any symmetric algorithm or key exchange algorithm for the application or for the use case. Then the security part will be strengthened. So you can use this cryptographic algorithm in your project. Once you understand the algorithm, then it is easy for you to solve any kind of problem. Thank you.
Thank you, ma'am, for answering those questions and for the great presentation. Thank you, ma'am. Over to you, George Janita.
Thank you, Miss Anita. Gratitude is the parent of all virtues. It is not joy that makes us grateful, it is the gratitude that makes us joyful. I call upon Miss Kartika to deliver the vote of thanks. Over to you, Kartika.
Good evening, everyone. This is Karthika from ECE department. It is my privilege to propose a vote of thanks and acknowledge the contribution of all those who worked tremendously to make this webinar happen. Thanks to Almighty God for making this webinar a grand success. My special thanks to our chief guest and resource person, Dr. S. Bhagavati Priya ma'am. Thank you, ma'am, for sharing your knowledge with us. We gained a lot of knowledge on hash algorithms and problems, which will be very useful for us to take up the university exam and also for the future. Thank you so much, ma'am, for spending your time and knowledge with us. Thank you, ma'am. And I would like to thank our respected principal, Dr. Sujata Anand. Thank you, ma'am, for giving us this opportunity to conduct this webinar. I would like to express my sincere gratitude to our beloved Vice Principal cum HOD, Dr. Navini Joseph, for words of encouragement and support and guidance. My heartfelt thanks to all our faculty members and student coordinators for their involvement and the willingness who made this webinar a grand success. I thank all the participants who showed up their interest for the webinar with utmost curiosity. Once again, thank you everyone for your presence. Thank you.
Thank you, Miss Kartika.